There is a building in Greenbelt, Maryland, where engineers are right now machining a mirror so precise that its surface variations are measured in picometers, distances smaller than a single atom. The machine they are building has a price tag that started at $4 billion and is already drifting toward 11. It has a launch date in the 2030s that almost no one inside the program privately believes anymore. And it has a mission statement that, if you read it carefully, makes a promise no telescope in human history has ever been engineered to keep. NASA calls it the Habitable Worlds Observatory. The press calls it the telescope that will prove we are not alone. But the contrast ratio it requires is harder than anything optics has ever attempted. The word biosignature has no peer-reviewed definition strong enough to survive a courtroom, and the timeline is already collapsing. Before we go further, tell me where you're watching from. What time is it where you are right now? And be honest with yourself for a second. Do you actually believe in your bones that humanity will confirm extraterrestrial life in your lifetime? Hold that answer. We're going to come back to it. Here is the central claim I want you to hold on to. The Habitable Worlds Observatory will almost certainly find something. It will detect signals. It will pull spectra out of planets nobody has ever resolved before. It will produce images that look to the public eye like proof. But something is not proof. A suggestive spectral feature is not a confirmation. A plausible biosignature is not life. And the entire gravitational pull of this story lives in the canyon between those two words. Because the press release version of this mission and the internal engineering version are not the same story. One is being sold to Congress. The other is being whispered in conference rooms at Goddard's Space Flight Center, where the people who actually have to build this thing are using words the public hasn't caught up with yet. Words like ambiguity, upper limits, statistical confidence interval rather than detection. What NASA is actually building is not the answer machine. It is the most expensive ambiguity machine in the history of science. And the public has been emotionally prepared for an event, a single defining moment, a press conference, a phrase that ends 60 years of waiting, that the physics of this telescope may never be able to deliver in clean form. So before we get to what HWO might find, you need to understand what they're telling you it will do. Read the official statements carefully, not the press releases, not the headlines, the actual documents. The 2020 Astrophysics Decadal Survey, the document that recommended this mission, does not say the Habitable Worlds Observatory will prove we are not alone. It says the mission will search for biosignatures on roughly 25 nearby Sun-like stars. Search, not find. And that single verb is doing more work than any other word in the entire mission concept. Because search is what you do when you don't know if there's anything there. The press took that word and quietly translated it into find. NASA did not correct them. That silence is the entire story of how this mission is being sold. Look at the rest of the language. Potentially habitable. Signs of life. Candidate biosignature. Each of those phrases has a technical meaning inside the astrobiology community that is dramatically narrower than what the public hears. Potentially habitable means the planet sits in a temperature range where liquid water could exist if a long list of other conditions are met. It does not mean habitable. Signs of life means a spectral feature consistent with biology, but also consistent with at least 2 or 3 non-biological processes. Candidate biosignature means we saw something interesting and we have no idea what it is yet. The public hears confirmations. The scientists know they are placeholders. Now look at the number, 25 stars. That is the realistic target list. 25 sun-like stars within roughly 10 parsecs of Earth, where the geometry, the brightness, and the distance all line up well enough that HWO can attempt a direct image. 25. out of an estimated 200 billion stars in the Milky Way galaxy alone. That is not a sample. That is a college seminar. That is the number of people you might invite to a wedding. The public has been led to believe this telescope will sweep the galaxy. It will not. It will stare, one at a time, at a handful of stars that happen to be close enough and bright enough to make the physics barely possible. Now compare this to JWST, launched in December 2021. Every single time JWST has produced a result that looked like a biosignature, that result has been quietly walked back within months. K218b in 2023, the dimethyl sulfide claim that briefly made headlines worldwide. By 2024, the consensus had shifted. The signal was weaker than reported. The molecule might not be there at all. The story did not get a retraction headline, it just faded. That is the template. That is exactly what HWO is being engineered to do, only at a scale and price tag that makes every walkback politically catastrophic. Here is the number that decides everything: 10 to the minus 10. 1 part in 10 billion. That is the contrast ratio the Habitable Worlds Observatory must achieve to directly image an Earth-like planet sitting next to a Sun-like star. The star is 10 billion times brighter than the planet. Not 10 times, not 1,000, 10 billion. To detect the planet at all, HWO must build an instrument that can suppress the light of the star by a factor of 10 billion, while leaving the much fainter light of the planet untouched. Nothing humanity has ever built has done this. The current state-of-the-art, on the best ground-based telescopes with the most advanced adaptive optics on the planet, is roughly 1 part in a billion. 10 to the minus 9. That sounds close. It is not. The difference between 10 to the minus 9 and 10 to the minus 10 is a factor of 10, an entire order of magnitude. To go from where we are now to where HWO needs to be is the same kind of leap as going from a propeller airplane to a jet engine. It is not an upgrade, it is a different category of machine. Here is what that number means in human terms. Imagine you are standing on a rooftop in Los Angeles at midnight. There is a lighthouse in Tokyo, 8,000 kilometers away. The lighthouse beam is on. Your job is to spot a single firefly hovering 1 meter to the left of that lighthouse. Through the curve of the Earth, through the atmosphere, through the optical noise of every city light in between. That is the order of magnitude HWO is being asked to handle. The instrument that has to make this work is called a coronagraph. Think of it as a surgical light blocker, a system of precisely shaped masks and mirrors that suppress the star's light at the exact spatial location where the planet would be. The mirrors must remain aligned to within a few picometers. A picometer is 1/trillionth of a meter, about the width of 10 atoms. If the mirror shifts by more than that, the suppression fails. Starlight leaks into the detector and the planet vanishes back into the glare. Now think about what could move a mirror by 10 atoms. A micrometeoroid impact. A thermal flex as the spacecraft rotates between sun and shadow. A reaction wheel spinning up. Vibration from a maneuvering thruster. Every one of these things on every spacecraft ever built happens routinely. On HWO, every one of these things is a potential mission failure. JWST is a hard mission at the edge of feasibility. HWO is fragile in a different category. One bad day and the mission's most important observations are lost. And the optics are the easy part. Here is the number nobody talks about in the press releases. When the Habitable Worlds Observatory finally isolates an Earth-like planet from the glare of its star, the number of photons it collects from that planet's atmosphere, per hour, per spectral channel, will be measured not in millions, not in thousands, but in single digits. A handful of photons. Sometimes one, sometimes none. The instrument is being designed to chase signals so faint that the difference between detection and noise becomes a philosophical argument, not an empirical one. Spectroscopy is how you read an atmosphere. You take the light from the planet, split it into its component wavelengths, and look for dark lines where specific molecules have absorbed specific colors. Oxygen absorbs at certain wavelengths, water at others, methane at others. To read those absorption lines with statistical confidence, you need enough photons to distinguish a real feature from random fluctuation. And HWO is being asked to do this with planets emitting almost nothing the telescope can see. The integration time estimates, published in peer-reviewed atmospheric retrieval studies, are sobering. To obtain a usable spectrum of an Earth-twin atmosphere around a nearby Sun-like star, HWO may need to stare at that single planet for 60 to 100 days, continuously. 60 to 100 days of telescope time pointed at a single target, accumulating photons one at a time. And at the end, the result may still be ambiguous. The error bars may still overlap with zero. Compare that to JWST. When JWST detected water vapor on the gas giant WASP-39b in 2022, it took roughly 12 hours of observation. 12 hours on a planet the size of Saturn, with an atmosphere so thick and hot that its absorption signatures are practically screaming. HWO is being asked to perform a task 1,000 times harder on a target 1,000 times smaller. The signal-to-noise problem is not incremental. It is categorical. This is what fragility means at this scale. The discovery is not blocked by a physical wall. It is blocked by statistics, by a noise floor that may be permanently above the signal level, by the brutal arithmetic of how many photons leave an Earth-sized planet per second, how many survive light-years of space, how many reach the detector, how many land in the specific wavelength channel where a biosignature might appear. By the end of that cascade, you are counting in single digits, single photons, per hour, per channel. And that is the fragility on one target. Now multiply by the size of the search. 25 stars sounds like a search. It isn't. It is a cascade of probabilities multiplied against each other until almost nothing survives. Start with the 25 Sun-like stars on the realistic HWO target list. Now ask, how many actually have an Earth-sized planet? The occurrence rate of Earth-sized planets in habitable zones, what astronomers call eta-Earth, is one of the most contested numbers in exoplanetary science. The estimates range from 10% to 50%. Take the middle. Call it 1 in 4. 25 times 1 in 4 equals about 6. Already the number is collapsing. Now apply geometry. To directly image a planet, the orbital plane has to be oriented so HWO can see the planet separated from the star. If we are looking edge-on, the planet spends most of its orbit hidden. The orientations are randomly distributed. Roughly half will be poorly oriented. 6 becomes 3. Now apply atmosphere. Even if the planet exists, even if the orbit is oriented correctly, the planet has to have an atmosphere thick enough to produce detectable absorption features. A planet like Mars would produce a spectrum that is essentially flat. Optimistically, half. 3 becomes 1 or 2. Now apply stellar variability. Even Sun-like stars are not perfectly stable. They flare, they spot. That variability gets imprinted on the planetary signal and contaminates the spectrum. For some target stars, the noise from the star itself may permanently exceed the noise floor required to detect a biosignature. 1 or 2 becomes a fractional expectation. This is the math the public has not been told. The Habitable Worlds Observatory, after $11 billion and 20 years of development, is being designed to attempt direct biosignature detection on what may turn out to be a single planet, or 0 planets. The expected yield, in the most rigorous published estimates, is approximately 1 Earth-like atmospheric characterization. Not dozens, not even a handful. 1. Compare this to Kepler. The Kepler mission, launched in 2009, discovered thousands of exoplanet candidates. But Kepler used the transit method, watching for the tiny dip in a star's brightness when a planet passes in front of it. That method tells us almost nothing about atmospheres. The Kepler catalogue and the HWO target list barely overlap. HWO starts almost from scratch, with a target list 100,000 times smaller and a far harder physical task. And even if the lottery hits, even if HWO sees something, the real problem isn't the telescope. It's what finding life actually means at the level of a single spectral line. Here is the thing nobody wants to say out loud. There is no molecule that means life. There is no single absorption line in any spectrum that, by itself, constitutes proof. Every candidate biosignature has at least one credible non-biological explanation. Every one. And the more carefully you study the list, the worse this gets. Take oxygen. Earth's atmosphere is 21% oxygen, overwhelmingly the product of photosynthesis. If HWO sees an oxygen line in the spectrum of a distant Earth-like planet, the headlines will write themselves. But oxygen can also be produced abiotically through photolysis, the splitting of water vapor or carbon dioxide molecules by ultraviolet light from the host star. On certain planets, oxygen can accumulate to atmospheric concentrations without a single living organism present. The peer-reviewed literature on oxygen false positives is now extensive. Methane has the same problem. On Earth, most atmospheric methane comes from biology, wetlands, livestock, microbial activity. But methane is also produced by volcanism, by hydrothermal serpentinization reactions in rocky crusts, and by geological processes with nothing to do with life. The answer requires knowing things about the planet's geology and interior that the telescope cannot determine. Then there is dimethyl sulfide, the molecule that briefly made headlines in 2023 when JWST observers reported a tentative detection on K2-18b. The press coverage was enormous. Within a year, the detection had been walked back. Independent reanalysis could not confirm the molecule was actually there. The molecule that briefly looked like a smoking gun turned out to be neither smoking nor a gun. This is what biosignature detection actually looks like in practice. Imagine sitting in a doctor's office. The doctor shows you a scan and says, "We found something." You ask what it means. The doctor says the shape is consistent with a tumor. You feel the panic. Then the doctor adds, it is also consistent with a shadow, a benign cyst, or a scanner artifact. You ask for a biopsy. The doctor says, we cannot do a biopsy. We will never be able to do a biopsy. That is the epistemic situation HWO is being engineered to produce. NASA knows this. The agency's own Biosignature Standards of Evidence framework, published in 2021 in Nature, lays out an explicit ladder of confidence that requires multiple independent lines of evidence. The framework is honest. It is also almost impossible to satisfy with a single telescope observing a single planet from light years away. Compare to ALH 84001, the Martian meteorite announced in 1996. President Clinton stood on the White House lawn and described possible evidence of past microbial life on Mars. 30 years later, the debate is unresolved. HWO's results will look structurally identical. Now, widen the lens. Everything we have just talked about assumes the telescope actually flies. And that assumption is getting weaker every year. The Habitable Worlds Observatory is being designed inside an agency that has not yet recovered from the project it just finished. And that project tells you everything you need to know about the project it is about to start. The James Webb Space Telescope was originally budgeted at around $500 million. By the time it launched in December 2021, the final cost was approximately $10 billion. That is a 20-fold overrun. The original launch date was 2007. The actual launch date was 2021, a 14-year delay. JWST was not a failure. It is one of the most successful scientific instruments in history. But the institutional process that produced it nearly broke NASA's astrophysics division. Multiple congressional reviews questioned whether the project should be cancelled. Other missions were delayed or descoped to absorb the overruns. That is the shadow HWO is being designed inside. Now apply the JWST multiplier to HWO. The early cost estimate is roughly $11 billion. Apply a 20-fold overrun, and you get a final cost that would be politically impossible. Apply even a 3-fold overrun, modest by recent NASA flagship standards, and you arrive at 30 to 35 billion. That is approaching the entire annual budget of NASA for one telescope, with a one-planet expected yield. The figure exists not because anyone believes it. It exists because a higher figure would not survive the next budget hearing. The schedule is collapsing in parallel. The publicly stated launch target is the early 2030s. Talk to engineers privately, and the number drifts toward the late 2030s. Talk to former program managers, and the realistic estimate is the 2040s. The contrast ratio technology has not yet been demonstrated at flight readiness. JWST's 14-year delay was not an anomaly. It is the pattern. Look at what else is happening around HWO inside NASA. Mars sample return was descoped in 2024 because cost projections crossed 11 billion. Constellation was cancelled before it ever flew. SLS took twice as long and cost 3 times as much as projected. The pattern is not bad luck. The pattern is structural. And there is a workforce problem nobody talks about. The engineers who built JWST are retiring. The institutional knowledge of how to design space-based observatories at the edge of feasibility lives in a small number of people now in their 60s and 70s. If you are watching this in your 30s or 40s, you may be in your 50s or 60s before HWO produces its first usable spectrum. If you are watching in your 50s, you may not see the result at all. Here is the uncomfortable truth about how flagship science missions get funded. The science by itself does not sell. The accurate description of what HWO can probably deliver, a possibly ambiguous spectrum of possibly one planet sometime in the 2040s, does not get an $11 billion appropriation through Congress. So the description gets adjusted. Not falsified, adjusted. The technical caveats get moved to the footnotes. The word search becomes the word find. The word potentially becomes the word will. And the press release contains a version of the mission that the underlying physics cannot quite support. Look at the rebranding history. The mission we now call HWO was, until recently, 2 separate concepts. LUVOIR, the Large Ultraviolet Optical Infrared Surveyor, was the ambitious version, with a primary mirror 10 to 15 meters across and a projected cost in the $24 billion range. HabEx, the Habitable Exoplanet Observatory, was the smaller version with a 4-meter mirror. Both were submitted to the 2020 Decadal Survey. Both were too expensive to fly. The Decadal Survey Panel did something unusual. It recommended a hybrid mission that did not yet exist. A 6-meter telescope, a coronagraph instead of a starshade, a price point engineered to be politically survivable. The rebranding was not scientific, it was budgetary. This is not corruption. This is how institutional science actually works when budgets are scarce. The agency cannot afford to tell the unvarnished truth, because the unvarnished truth does not survive a congressional budget hearing. The public-facing version emphasizes the possibility of finding life because that possibility generates funding momentum. The internal version is far more modest. Both exist simultaneously. The gap between them is what we are talking about. Compare to pharmaceutical trials. When a drug company announces promising Phase 2 results, the language is carefully constructed to maintain investor confidence. The trial may have shown a small statistical effect in a narrow subgroup. The press release describes encouraging signals of efficacy. Both statements are technically defensible. They leave the listener with very different impressions. Compare to Apollo. In 1961, Kennedy promised the moon by the end of the decade. That timeline was not a forecast. It was a deadline weapon. HWO's 2030s timeline is the same rhetorical device, 3 generations later. But the political environment is not the same. The funding stability is not the same. The deadline weapon is being used without the institutional conditions that made it work the first time. I want to be clear what I am not saying. I am not saying NASA is lying. I am not saying engineers are incompetent. What I am saying is that the framing is doing emotional work the underlying physics cannot fully support. Every time HWO produces an ambiguous result, trust will erode. The cycle compounds. Now widen the lens one more time. Because the question HWO is being built to answer is not really a scientific question. It is a civilizational one. And the more carefully you examine it, the worse it gets in every direction. There is no comfortable outcome. No result this telescope can produce leaves humanity in the same epistemic position it occupies right now. Every possible answer breaks something. Consider the 2 main scenarios. In the first, HWO finds a clean biosignature. The math says this is unlikely. But suppose it happens. The telescope detects, on one of those 25 target stars, an atmospheric signature that survives every check, every reanalysis. The implication is staggering. If life exists on one of the 25 nearest Sun-like stars, then life is not rare. Life is everywhere. The galaxy contains, by simple extrapolation, billions of inhabited worlds. And the moment you accept that conclusion, the Fermi paradox sharpens into something close to a scream. Where is everyone? Why have we never heard a signal? The great filter argument, developed by Robin Hanson in the 1990s and extended by Nick Bostrom, says that something prevents the path from simple life to interstellar civilization. The filter is either behind us, meaning humanity has already passed the hard step, or it lies ahead of us. If HWO confirms that life is common, the probability that the filter lies ahead increases. Because if abiogenesis is easy, the hard part isn't getting started. The hard part is surviving long enough to be seen. Now consider the second scenario. HWO finds nothing. 20 years of observation, the most precise instrument ever built. Every spectrum comes back consistent with sterile chemistry. The implication is the opposite and equally heavy. It means Earth-like worlds with detectable life are rare even among our nearest neighbors. It means humanity may be alone in a way we have never seriously believed. Not philosophically alone, physically alone. Across the volume of space we can actually reach with any telescope humanity is ever likely to build. Both outcomes leave the species in a worse epistemic position than the comfortable middle we currently inhabit. Right now, we live with a question. The question is open. The future is undefined. HWO threatens to close that ambiguity, and the closure, in either direction, is harder than the opening. There is a 1960 report commissioned by NASA from the Brookings Institution that addressed exactly this question. The report warned that the discovery of extraterrestrial life could have profound disruptive effects on human societies. Religious institutions would face theological challenges. Cultural frameworks built on human exceptionalism would have to be revised. Humanity has spent 60 years asking this question. We have not spent any serious time preparing for the answer. The telescope is not really pointed at the stars, it is pointed at us. Let me consolidate. The Habitable Worlds Observatory requires a contrast ratio of 1 part in 10 billion. A leap of an entire order of magnitude beyond any optical instrument ever flown. The photon counts from its target planets will be so low that integration times stretch to 100 days per target, with error bars that may never close. The realistic target list is 25 stars, filtered down to an expected yield of approximately 1 Earth-like characterization. The word biosignature has no peer-reviewed definition strong enough to deliver a clean answer. The cost estimates will almost certainly multiply. The schedule is collapsing toward the 2040s, and the question the telescope is being built to answer is one humanity is not psychologically prepared to receive in either direction. That is the case. And now, let me return to where we began. Picosecond precision mirrors, a $4 billion machine, a stated mission to find life. Read those 3 things again with the weight of the last 9 chapters behind them. The picosecond mirrors are the most fragile optical system humanity has ever attempted to fly. The $4 billion price tag is an entry fee, not a final bill, with the realistic cost almost certainly multiplying into the tens of billions. And the mission to find life is, when you read the technical documents, a mission to search for ambiguous spectral hints on a target list smaller than a college seminar, with an expected yield of approximately 1 possibly inconclusive result. This is what I want you to hold on to. The Habitable Worlds Observatory is not the telescope that will prove we are not alone. It is the telescope that will prove how unprepared humanity is for the question itself. It will produce findings too suggestive to ignore and too weak to confirm. It will generate decades of academic argument with no clean resolution. It will deliver, at enormous cost, the most expensive ambiguity in the history of science. I want to say what I am not saying. I am not saying the mission should not be built. Build the telescope, fund the program, run the mission. The data will have value. The argument is about honesty, about what we are actually buying. There is a narrow form of hope that survives this analysis. Not the hope of a clean discovery, something quieter. The hope that the discipline of building this instrument and the maturity required to interpret its ambiguous results will force a kind of growing up that humanity has not yet done. The acceptance that some questions do not yield clean answers. The humility of confronting a question larger than our tools. The telescope is a mirror. What it reflects back is not really the cosmos, it is us. Asking a question we may not survive the answer to, we are not alone, or we are. The telescope will not tell us. It will only tell us that we asked.